Episode 15, Atomic Clocks, Measuring Time Itself. By the middle of the 20th century, humanity had built clocks of extraordinary precision. Pendulums had reduced errors from minutes to seconds. Quartz crystals vibrated tens of thousands of times each second and could keep time to within a few seconds each month. For most people, quartz clocks seemed almost perfect. Yet scientists, astronomers, and navigators needed something even better. They wanted a clock so stable that it would hardly change at all, not over days, months, or even years. The answer lay not in gears, springs, or crystals, but in the atoms that make up the universe itself. Scientists had discovered that atoms behave in a remarkably predictable way. When supplied with the right amount of energy, atoms absorb and emit radiation at very precise frequencies. Unlike a pendulum, an atom does not wear out. Unlike a quartz crystal, it does not slowly age or drift. Every atom of a particular element behaves in exactly the same way as every other atom of that element, wherever it is in the universe. This suggested an astonishing possibility. Instead of measuring time by counting the swings of a pendulum or the vibrations of a crystal, perhaps time could be measured by counting the oscillations occurring within an atom. During the 1940s and 1950s, scientists experimented with several different elements, but eventually one stood out above all the others. It was an element called caesium. The caesium atom oscillates at an incredibly high frequency, vibrating more than 9 billion times every second. In 1967, scientists around the world agreed that this would become the new definition of the second. From that moment on, a second was no longer based upon the Earth's rotation. For the first time in history, humanity was no longer measuring time using the movement of the sun, the moon, or even the Earth itself. We were measuring time using the fundamental properties of matter. Inside an atomic clock, caesium atoms are heated until they form a beam traveling through a microwave chamber. Scientists adjust the microwave frequency until the maximum number of atoms respond. Electronic circuits continually correct the signal, locking it onto precisely the right frequency. Once this happens, the clock produces an incredibly stable pulse that can be counted to measure time. The result is accuracy almost beyond imagination. A modern caesium atomic clock would gain or lose only about 1 second in tens of millions of years. Even newer optical atomic clocks are being developed that may eventually lose less than a second over the entire age of the universe. Such precision may sound unnecessary. After all, nobody minds if a wristwatch is a second fast after a month. But atomic clocks have become essential to modern civilization. Every GPS satellite orbiting the Earth carries several atomic clocks on board. These satellites continuously broadcast signals containing the exact time at which they were transmitted. Your phone or satellite navigation system compares these signals from several satellites and calculates its position. Because radio waves travel at the speed of light, even an error of 1/1,000,000th of a second could place you hundreds of meters from your true location. Atomic clocks are also used to synchronize telecommunications networks, financial markets, scientific laboratories, and the internet itself. Every day, billions of electronic devices depend upon timing signals ultimately derived from atomic clocks. Ironically, the Earth itself refuses to keep perfect time. The gravitational pull of the moon, changes in the atmosphere, and even major earthquakes slightly alter the Earth's rate of rotation. To keep our clocks aligned with the position of the sun, scientists occasionally add a leap second to atomic time. Today, researchers are developing even more advanced clocks based on elements such as strontium, ytterbium, and aluminium ions. These clocks may one day be so sensitive that they can measure tiny differences in gravity, detect movements deep within the Earth, and perhaps even help answer some of the greatest mysteries in physics. For thousands of years, people looked towards the heavens to understand time. Now, we look inside the atom itself, and by doing so, we may have come closer than ever before to measuring not simply the passing of time, but the very fabric of the universe. In the next episode, we discover how Albert Einstein overturned centuries of thinking by revealing that time does not flow at the same rate for everyone, and that motion and gravity can cause time itself to slow down.